All right. Can you guys? Hello, everyone. Welcome to this session called the Dancing Robot. My name is Tommy.
My name's Philip.
And we are physicists at UCSF in the Department of Radiation Oncology. And we're going to talk to you a little bit about how we use radiation and the technology to treat cancer and save lives. Thank you for joining us today. I hope everybody is doing well, and a big shout out to the Bay Area Science Festival for helping organize these sessions, which have been incredibly fun so far. So let's jump right into it. Okay. So we're going to be talking about a robot which can dance, but it doesn't just dance. This robot, which is shown in the image over here, is called CyberKnife, and it is used to treat cancer with radiation. So this part that's shown in the image is called the head of the robot, and it generates X-rays that are used for therapy. Now, the robot does not stand still. Similar to dancing, it has to move. And it can move in different angles to use radiation in this direction, or maybe in this direction, or this direction, or another direction. By shooting radiation in different ways and from different angles, we can ensure that we are targeting the disease effectively while avoiding any other tissue that could be nearby. What you see here is a patient laying down on a couch, and the patient lays down very still. And as they lay there, the robot will move around to deliver this medicine. We're going to be showing you some videos, and we're going to talk a little bit about how this works. And then we'll show you in the room, we'll show you a real demonstration of the robot moving, which we have in the background here. If you have any questions, feel free to type them in the chat, or maybe raise your hand or give us a thumbs up if you want to do that. All right.
So first, we'll talk a little bit about what actually radiation is. So hopefully you can see here on this slide, we have this what we call an electromagnetic spectrum. So what we're talking about now is radiation. And it's actually, can everybody hear us okay? I think we can hear. Use this one too. Okay. So we're talking about radiation, and that's what is going to be coming out of this CyberKnife machine that Tommy was talking about, the head of this CyberKnife machine. So on this slide, we're talking about radiation. And this, hopefully, maybe some people have seen our previous sessions at the Bay Area Science Festival where we talked about radiation. And a lot of you might already know what radiation is. And the truth is, radiation is always around us. We might not feel it all the time, but radiation is passing through us right now from a bunch of different sources. So we're going to go through some examples. Not all radiation is bad for you. And when you're in the car, for instance, when you use a radio, your car is receiving radio waves to play your favorite songs on the radio. And radiation acts like a wave, and these waves can be shorter or longer or bigger or smaller, and that's what determines what we can use it for. So radio wave is a lot longer, and it doesn't hurt us. And everything, or another example of radiation is microwaves. So whenever you use a microwave oven, these waves are a little bit shorter than radio waves, and they actually vibrate the molecules in your food to heat it up. And as you get further on the right of the spectrum, the waves of radiation get shorter and shorter and faster and more energy and more force until we get to this visible light, which we see you're seeing us right now with visible light. These waves are still a little bit shorter, but they generally don't hurt us. But as soon as you cross this line, we call it ionizing radiation past this visible spectrum. Radio waves and microwaves we call non-ionizing, and that's because they don't have enough energy, they're not strong enough to give us a sunburn. So ultraviolet waves are an example of what comes from the sun, and that's how you get a sunburn if you don't put on sunscreen, you stay outside too long. But as we get further and further to the right on the spectrum, we get to X-rays and gamma rays. And these are actually the types of waves. Oh, I forgot to show our example of visible waves. When we have Halloween, you make a jack-o'-lantern, you get visible waves of light. But all the way on the right here, we get to our therapeutic radiation. And that's what's actually coming out of our CyberKnife, our dancing robot. And these are radiation beams that are high enough energy to target cancer cells, bad cells in your body, to actually try and treat and cure cancer. So that's kind of a general idea of what radiation is. Not all radiation is bad for you, and we actually use high energy radiation to treat cancer patients. And that's exactly what we use here. We have a picture of a person's brain, and all of these little beamlets are little beams of radiation that come out of our dancing robot here and target the cancer cells in someone's brain. And we avoid treating the healthy parts of someone's brain with radiation. We only target, this dancing robot is really smart and can see in the patient's brain and see the cancer cells. And we want to target them with high energy radiation. So I'm going to talk a little bit more about how radiation actually treats cancer. And the key is actually in the DNA. So I don't know if anyone knows what DNA is, but everybody has it. It's what makes you, you. Every cell has DNA, good cells and cancer cells. And a really cool thing about DNA is that it can copy itself. The problem with cancer cells is that DNA copies itself too fast, too much, and it starts to overtake healthy cells in the body. So what we can do, we found, a lot of smart people found, a lot of scientists found that if we target radiation at DNA, this is kind of an example of what DNA looks like. It's kind of like a double, it's kind of like a ladder spiraled in on itself. And what we can do is shoot radiation beams, and it can break DNA strands, these ladders. And if we hit DNA within a cancer cell, we can stop it from copying in a bad way. And we can actually kill the cancer cells that way. And we have our little radioactive man. So we have a team of physicists like ourselves, and who you'll meet throughout this talk, that use our friend, our dancing robot, to target DNA in cancer cells. And it's really cool because you can kind of see DNA is actually really small. You definitely can't see it. I don't know if anyone knows how small a nanometer is, but here we see DNA is about 2 nanometers wide, and that's about 40,000 times thinner than one of your little strands of hair. So that CyberKnife, what we call our dancing robot, can shoot really precisely and target that DNA. And that's what we're going to kind of show you all how it does that. So we have a little video, a little animation that will show how this works. So hopefully everyone can see this video. Yeah.
All right, so in this video, the beams of radiation are targeting the tumor, and these beams are coming out of our dancing robot, our CyberKnife. And as the patient lays there, what we can see is the robot safely moves around the patient, and then it delivers some radiation. And then it will do this in consecutive steps until we deliver enough radiation to kill the cancer. This is the mechanism that Philip was talking about in terms of destroying the DNA. And if we do this enough times, we can see that the tumor will go away and the patient will be cured. Radiation is used not only for brain tumors, but it's also used for other parts of the body. You can treat it in your chest, in your lungs. You can treat your abdomen. You can treat various parts of your body with radiation. So this video shows how this robot moves. And over here. Okay, so that video is a great illustration. Before we go over here, maybe what we want to do is give you an example of what it's like when a patient comes in and is treated for radiation. So hopefully you can see my camera, which is spotlighted on my screen. And Philip will pretend to be a patient. So we would first set up the patient for radiation. Perfect. So Philip goes on the couch. And then our nurses help position the patient in a way that we've planned for delivering the radiation that is safe and effective. We use devices which are called immobilization devices, and like this knee sponge over here to make sure that the legs are comfortable and don't move. We also use different parts around the neck. So here is a little neck cushion that's used to immobilize the patient. And it's very important that we ensure the location of the patient to deliver radiation safely. And we can also use other types of immobilization devices like this mask that has been specially fitted for each patient. And this will ensure that the patient stays in the same location and does not move. And throughout this entire process, the patient lays down comfortably. Treatment can take up to 30 minutes. And as the patient is laying there, the CyberKnife robot dances around them. And the robot will move into each location, which we call nodes. And these nodes have been predetermined and calculated so that we can ensure the radiation is going to the right place. So here you can see the robot is slowly moving into its precise area. And as it does this, it's the radiation would come out of the robot's head, which is shown here, and it's on a robotic arm, which helps move it to its precise location. And this robotic arm has 6 degrees of freedom so that the robot can rotate, position itself, use each specific angle, and then shoot a very narrow beam of radiation so that it can kill cancer and spare normal tissue. During treatment, which could take up to 30 minutes, we also use X-ray imaging. There are 2 X-ray tubes which are located in the ceiling. So there is one X-ray tube and there is another X-ray tube up there. And these X-ray tubes shoot X-rays onto the floor. So there is an X-ray detector on the floor here, and there's another X-ray detector on the other side. And as the patient lays there, X-ray images are required periodically, sometimes every 30 seconds or every minute. And these are used to ensure that the patient is in the same position as set up during treatment. Sometimes you might sneeze, or you might cough, or maybe you have an itch and you need to move a little bit to adjust yourself. The robot can detect these small motions that we all do naturally. Not to mention, we are always breathing and our diaphragms are moving up and down and our lungs are filling and emptying out air consistently. So the CyberKnife robot will detect those motions, and then it will correct the radiation beam so that it can still target the tumor even when there is motion present. And the ability to move around and have different angles, planes, nodes of freedom really make this system very effective at treating tumors like in the brain or in the spine or in the lung. And that way we can ensure that a therapeutic dose is going to a tumor, which is a high amount of radiation, but that it is safe for the rest of the body. So that is a little bit of a live demonstration of what a radiation treatment might look like for a patient. Awesome. Does anybody have any questions in the chat that we might be able to answer? Good job, Philip. Yeah, so there was a question about the size of the radiation beam that CyberKnife shoots out. So the sizes can be as small as 5 millimeters in diameter or up to as big as 60 millimeters in diameter. And what we do is we use different sizes of beams to make sure that we can cover the entire tumor. And in a little bit, we'll go into more detail at how that is done. So here is an example of a cone, which is a 5 millimeter cone. So that will block all the x-rays except the ones in that tiny hole. So that is how small the beam is. It is almost the size of a needle that would attach onto the linear accelerator that CyberKnife has. In addition to that, we perform a lot of quality assurance tests to make sure that the dose is delivered accurately. So could you grab the Phantom over there and bring it over? Perfect. So we do want to vaporize the tumor. We want to ablate it, we call it. So we want to deliver enough dose, kind of like you cook things in your microwave. You want to completely remove it. It's almost like surgery, but surgery from the outside without cutting inside the patient. So we have what we call these objects that we can run tests on. So this is used to copy a patient or to pretend as if this was somebody's head, skull, brain. And we can deliver radiation to this plastic and measure it, and to ensure that our system is accurately delivering dose. So these are some of the tools that we use with CyberKnife, and we can ensure accurate dose delivery. Are there any other questions that we might have missed in the chat?
Yeah, so there's questions about why does the CyberKnife have to move around? Why can't it just stay in one position?
Philip, would you like to answer that question?
Sure. Can everybody hear me now? Very good. So the CyberKnife has to move around because it actually, using those X-ray imaging tubes, is able to track where the bad tissue, the bad cancer cells are in the patient. And since patients are breathing, sometimes that cancer is moving inside the patient. And there's actually a lot of software behind this robot that actually is able to find the best possible position that the CyberKnife can place itself to be able to miss important tissues. So you don't want to hit healthy parts in your brain. You want to just hit the bad cells. So the CyberKnife, the really good thing about CyberKnife that Tommy was talking about is it can move in 6 degrees of motion and all around the patient and miss all of the important healthy tissues. That's really the important part. We want to deliver the radiation as much as we can to the cancer while missing and sparing, we call it, healthy tissue. So that's really the key that we want to do in radiation therapy for each patient.
Yeah, that's great. Yeah, I think we can show you guys some more videos that we have. These questions have been great, so keep asking them in the chat, or feel free to unmute yourself if you can and ask us any questions. Yeah, by spreading out the radiation using beams from different directions, like Philip said, we can avoid tissue that we don't want to ablate, we don't want to vaporize. We only want to vaporize the bad cells. We want to vaporize the DNA there using ionizing radiation. So here is a video of how CyberKnife can track motion that's like breathing motion that's happening inside patients. So what we have here is a little phantom on a stage. We have something that's moving around. And as it moves up and down, what you'll notice is that the robot, I know it's very subtle, but you can see that the robot is also moving with the stage. And the stage is the motion amplitude is about 1 to 2 centimeters. So these are very small movements, only a couple of centimeters. So this robot can track with an accuracy of less than 1 millimeter. So it can detect motion that's 1 millimeter or less, and it can adjust its beam so that it is always following the object of motion.
These are all good questions.
Yeah. Does anybody have any other questions in the chat? It's a very good question, and we'll get into a little bit of that in a minute here, because that is one of the main responsibilities of a medical physicist, is to ensure that we are avoiding this tissue by the right amount. And the short answer is that different parts of our body have different tolerances for how much radiation they can receive, and we control and adjust to ensure that we are below those safe levels of radiation. So that is really the main goal of radiation therapy, and medical physicists, that's what they do. We work with doctors to make sure that the equipment, which uses medical imaging, which uses all of this cool physics, that is delivering a safe amount of radiation to vaporize the tumor while sparing normal tissue. And it's very complicated to describe all of the factors that go into it, but there are tolerances which we know and we monitor, and we make sure that we are below those tolerances. All right, those have been great questions. And maybe before we transition to the second part of our talk, we want to show you a video of a time lapse of what the dancing robot looks like when it's actually dancing. So this is the dancing robot. And this is why we call it a dancing robot, because it actually looks like it's dancing when it's treating the patient. And we have the phantom there that we're doing this test with, the phantom that we showed earlier. Phantom which we showed earlier. That's awesome. And so, you know, that's a little bit about the dancing robot. And Philip and I, what we like to do when we're doing physics is we like to also do the robot dance.
You guys can do the robot with us.
You guys can do it with us, because that is what the dancing robot does.
I have a question.
Yeah,
The question is like, can it heal, treat all kind of cancers? Any cancers?
Yeah, so it can treat all types of cancers. We do work with, you know, like I said, lung cancer, prostate cancer, cancer in the brain. The process of treating cancer is complicated, and radiation therapy is a part of it. So only about 50% of all cancers are treated with radiation therapy. Some cancers are treated with other medication, such as chemotherapy and other drugs. And sometimes they are used in combination as well. But radiation therapy is a very attractive choice in medication for these cancers because it doesn't involve surgery. And it's a very localized, targeted way of delivering medicine, which is not possible with all drugs. So when you take chemotherapy, it affects your entire body when you might only have cancer in the lungs. If you wanted to do surgery, you would have to operate on somebody to target something local. And what we do is, depending on a patient's conditions and their type of cancer, radiation is sometimes perfect for delivering local radiation and local treatment with radiation that way. So that's a great question. Yeah, and CyberKnife, this dancing robot, it's one of my favorite machines. But there are other machines that we use in radiation oncology to deliver radiation. And these are machines that sometimes produce radiation or use radioactive sources to deliver radiation in a safe way. So this is just one example, but there are many other types of machines. And to talk a little bit about the career of medical physics, and to talk a little bit more about the career of medical physics and the equipment that goes into it, we're going to have Manju, who is going to be telling us about what a medical physicist does and a little bit more information on how we treat cancer with radiation, to answer all the questions that you guys brought up, which have been great. But we wanted to show you our dancing robot because it's such a cool machine. It's so fun. And we'll pass it on to Manju to tell us more about, medical physics.
Hi guys, it has been a very exciting experience sharing what we do with everybody. So I am going to talk a little bit on kind of easy stuff. So what our radiation oncology field is and what we do. We are medical physicists. We just wanted to touch a little bit on that. So can you all see my screen? Okay, cool. So as Philip and Tommy explained to you guys, like, you know, cancer is a kind of a bad cells that are growing in our body. And in our field, we try to kill them with the radiation. And here is a small video showing like a picture of what happens.
The most common type of head and neck cancer, called squamous cell carcinoma.
So they are showing a kind of a cancer which grows in the sinuses. So usually what happens is that cancer cells are bad cells which start growing at their own fast pace, and then they start interrupting the normal functioning. And so whenever a doctor tries to cure cancer, they look at various aspects. Some of them are like at which location the cancer is and what stage. By stage is usually when the cancer grows. Typically, we have divided it into 4 stages. When the cancer is very small, and that is called the stage 1 cancer. usually that type of cancer can be taken out of your body through surgery. And when it starts branching out into your body, then it goes to stage 2, stage 3. And then when it gets very, very bad, it's everywhere, mostly in your body, then it can go to stage 4. In those cases, we generally pair radiation with other methods. So as I said, so depending upon the patient's age and how far the cancer has spread. So in case of the radiation therapy, we use, just like our CyberKnife, we are using very high radiation to treat the cancer. And the goal is to deliver radiation to all the bad tissue and to spare all the healthy tissue nearby. And that is the stage when the role of a medical physicist comes in. We want to make sure that what the doctor has prescribed for the treatment, it is being delivered accurately to the patient. So what you saw here is an external radiation, but we do have some kind of internal radiation in which we inject small isotopes into the tumor. And these radiations kill right at, they are at the site of the tumor, and then they kill the tumor cells. So slowly, so as an effect of this radiation, this thing is usually delivered throughout a course of few weeks to 4 weeks, depending upon what type of cancer patient has. And if everything happens, so we are able to cure the cancer. So how do we cure? And I think there was an interesting question when they were asking which device or which LINAC. LINAC is a linear accelerator that we use. And just like you saw today is the CyberKnife, but at UCSF, we have other LINACs which we use to cure cancer. There is another one. So CyberKnife is very good when you want to give radiation to very localized tumors. As Tommy mentioned, that the biggest size is 60 millimeter. But if your tumor is spread out, which is of the order of few centimeters, then you would need a linear accelerators that have a larger field size. And for those, we are using TrueBeam, which is at one of our other sites. And besides that, we also have a Versa, which is, these are different type of linear accelerators from different vendors. At our Mount Zion campus, we have Electra Versa, which has a larger field size than CyberKnife, but it is also used for giving very high radiation dose. And here in this picture, you will see how the precise radiation is going through the linear accelerators, so that it delivers radiation only where the tumor is, as the gantry is going through the body. All right. So when we talk of the field of radiation therapy, it's not just medical physicist or doctor. We are a team. We all work together to cure cancer. And here is a small map of how we work among different specialties. The first, when the patient is diagnosed with cancer, so patient comes to the doctor, and doctor is the one who prescribes a certain kind of radiation dose. Now, in this whole process, nurses, like you guys must have gone to the doctors, you see nurses also are there along with the doctor. So in our radiation therapy, we do have nurses which help the doctors and the patients in the routine health checkups, and if they have any general radiation related questions. And then we have therapists. Therapists are the professionals which are specialized to deliver radiation. And so they have to get certified training And so they are used, the therapists work during the CT scan process, in which I think we had a talk on the imaging in which you saw like how a CT scanner works. So therapists work in that step, and they also work during the radiation delivery. And then once, so therapists are going to scan the patient and make sure that if some patients have motion management, so therapists are also handling that part. And after that comes the dosimetrist. So when a patient comes in our clinic, they might not see the dosimetrist, but they work backstage, but they do a prime part. They are a prime part of our process, and their purpose is to create a plan which matches the intention of the doctor. So what doctor wants, they try to create the same kind of map. Say if they want to deliver a certain amount of radiation to the tumor, and they want to spare the normal tissues. That's the job of a dosimetrist, and we use various planning softwares to do that part. And then comes the role of a physicist. So we are called medical physicists. I would say like we are basically, all of us are physicists who like to work with the patients. And so while doing that, our main goal is to make sure that the linear accelerator is working right. So we work with all the people in our clinic to make sure what doctor wants is being delivered right to the patient. And sometimes when doctor has questions with the physics aspects of the radiation, we are there to help them. So let's see an example. So, when the first step where the role of a physicist comes in is when we install a linear accelerator. So we buy from a vendor a linear accelerator. Right from that step to the first day of the treatment, we are there and we are working day and night. Our residents and the physicists, they make sure that what the vendor told is actually working that way. And how do we do that? So we bring all the fancy tools which physics are very proud of. These we couldn't give you guys. I think because of COVID, you guys couldn't come in, but I think it would be. We wanted to show you a virtual layout of what are the different tools we have. So what you see here is a tank of water, which we use to make sure that, so this one is filled all the way with the water, and we scan. We have different type of devices. They are called ionization chambers that record the amount of radiation coming from the linear accelerator. So we make it go to a certain depth and sidewise to make sure that it is actually what we think it to be. And the second part comes in. So once, here I want to say that we are the ones who actually sign off the machine. Without a physics signature, machine cannot be released. And the second part that our role comes in play is during the validation of the plan process. So dosimetrists are the ones who actually create plans, but we want to make sure a plan that is pretty on the paper is actually looking good, is actually right when it is will be received by the patient. And to do that, we have a bunch of phantoms that we use, and we deliver the same amount of radiation that was planned for the patient on the phantom to make sure it is right. And we do have to sign off on this before you start treating the patient. All right, and then the third thing which I wanted to highlight is we are always there working with the doctors. Usually doctors have some questions regarding the physics aspects, and it can be like they want to do certain type of treatment, but they are not sure if it is even doable. And physics are always there to answer their questions. And sometimes we have to do our own research to make sure that what the doctor wants is actually possible to be delivered. All right, so I think like after this, I just wanted to give a small tour of our, so at UCSF, we have 3 different sites, and each site has a different linear accelerator, and we have our residents going a virtual tour of the 3 sites, and I wanted to just share with you guys. So today we are at the Mount Zion campus, which you will be seeing first at in this video. So here is Matt, he's one of our residents. So this is the CyberKnife that you guys just saw in the demonstration. So we also have a chemotherapy. We also have a chemotherapy unit. And then we have a Versa HD. So this is showing you the backstage of the Versa. And this is another accelerator, which is an old Oncology. So another good thing I wanted to highlight here is that even though we are very, spread in the San Francisco area, but the UCSF provides a good transportation service. So you can hop off any of the UCSF buses to go from one side to the another. So now Tommy, who's right here, he's showing a virtual tour of our Parnassus campus. So this is the DOSI space where people are, dosimetrists are planning. And here you see all of our residents. So even before the delivery of patient treatment and the physics, we always have chart rounds. In this, we have the team of doctors, dosimetrists, and residents, physicists. We all discuss about the quality of the plan, if it makes sense, or if there are any suggestions. And what you're seeing here is view of our conference room, where we generally discuss the patient treatment. And from here, we are going to go to the CyberKnife. So CyberKnife is also used for precise treatment delivery of mostly for brain cancer patients. And it is using single gamma ray energy of cobalt source. This is the CyberKnife. So what you're seeing here at our Parnassus campus, we have a TrueBeam linear accelerator. So the CyberKnife has a maximum field size of 60 millimeter, but TrueBeam STX has a field size of 20 centimeters. So if we have larger lesions, you can use the TrueBeam STX at Parnassus. So now we are going to the Mission Bay campus. Sorry, guys. Okay. So at Mission Bay, we have 3 TrueBeam Linux, which are the field size of them are even larger than STS. It is about 40 centimeter as a max field size. So this is our physics storage area where you can see all the fun tools that we work on to make sure that the right amount of radiation is being delivered. And here is the suite of our residents. And here is our physics space at PCMB. So I think like once this COVID ends up, you guys are more than welcome to tour us and see what we do. And this is the dosimetry space. And in our free time, we do like to play chess around. These are the CT scanners that we have. This is a hyperthermia, which we use high temperature to kill cancer. And that is it. So that was a quick tour. So I think like you guys are more than welcome to come in and visit us. And I think we can, I will stop the screen share and then we'll be happy to answer the questions if you have.
Yeah, Manja, there was a question about what type of radiation we're using. Could you speak a little bit about that?
Yeah, so depending upon which linear accelerator we are using, so we use mostly photons for treatment, and so their energy is in the terms of mega voltage. So for photons, we are using like 6 to 10 to 18 mega voltage, but we are also using electrons for treatment, and they also vary from 16 to 18 mega electron volt. And we also use the gamma knife that is at Parnassus. It is using cobalt, which is a gamma ray emitter of about 1.3 MeV.
That's great. And I guess, are there any other question? So does Gamma Knife give gamma X-rays? And how safe is Gamma Knife? Talk a little bit about Gamma Knife. Yeah, so, very briefly.
So Gamma Knife gives, it emits the 1.3 MeV cobalt gamma rays, and it kills the tumor. That's the whole purpose. So we have Gamma Knife, like the way you guys saw in the CyberKnife, we have tiny cones for the Gamma Knife as well. So the cones are used to direct that precise radiation right on the cone, right on the tumor. So it does kill the tumor. Was that the question?
I think that's good. I wanted to ask you another question. What makes somebody go into medical physics? You feel like, you know, like, why did you go into medical physics? And what do you like about medical physics as a career?
Yeah, so that's a very interesting question. I think this applies to all of us. So I did my PhD in nuclear physics. So, you know, I like physics. That's why I am working in the, you know, I did my PhD in physics. But the cool thing about medical physics is that you get to work on the cancer patients. And if you are really into patient care, then you should choose the field of medical physics. But another good thing about medical physics is that you see your results right away. So by the end of my day, every day when I'm working on plans and doing the QA, I feel so contented that today I did something good and made sure to save the life of a patient. It's a very rewarding profession in that sense. And I think like we can ask others as well around. I think.
Sure. Why don't we can introduce our team?
I think we will use this time to introduce everybody.
Why don't we all, and then if anybody has any questions, please feel free to ask in the chat. Philip and maybe Philip, I think you can leave it here and we can aim it down that way. So there's a large group of physicists at UCSF, and we are just some of them who work on what Manju described. And maybe we can introduce ourselves and just say hello. So again, my name is Tommy. Yeah.
Sorry, we're like passing around the microphone. My name is Philip. Oh,
maybe we can pass around the computer. Yeah, sorry. I'm sorry. Can everybody hear us?
Pass around the
Hi, I'm Martina. I am Ben. Hey, I'm Manju and you can call me. Hi, Emily.
Sorry. Hopefully everybody can hear each other. Sorry. Does anybody have any last questions before we all start doing the robot?
What is the success percent of treating patients with CyberKnife than chemo? It's something that varies between different types of cancers and treatments. And there are certain types of cancers that you would treat with CyberKnife alone. And then there are certain types of cancer that you would treat with chemo alone. And then their success rate varies between the two. What we do is we consider both options. So we consider the success rate of treating with chemo versus the success rate of just CyberKnife or both. And we choose the one that has the highest success rate. But I'm going to ask everybody to come back into our scene because as we say goodbye, and I want to thank you all for joining us. I hope you've enjoyed our session of the dancing robot, and happy dancing, everyone! Everybody do the robot. Oh.
Feel free to do the robot with us.
Please have the video.
Hopefully you all enjoyed that. Feel free to reach out to Radiation Oncology at UCSF if you ever want to come visit us with in the future.
You're welcome.
You're welcome to come. Are we good?